Hello, this is a blue LED being driven from this 8.1 volt power supply through an ideal diode, and you can see that every couple of seconds the LEDs go dim for a short period of time. So why is that? Well, I'll explain. I'll come back to this nearer the end of this video. So diodes, these are electronic components that act as a one-way valve for current. So you can pass a current from the anode through to the cathode, but you can't pass a current back the other way. This one is a small signal 1N4148 type diode. This is a 1N4005, I think it is. And this is a Schottky diode, 90SQ035, 9 amps with a 35 volt reverse bias voltage. So although diodes work as a one-way valve for current, it'll only pass from anode to cathode, not the other way. They're far from perfect. One of the major problems is the forward voltage drop. So once you get to the point where enough current is flowing through the diode, you've got a voltage difference between the cathode and the anode. And the problem is, when you've got current flowing through a diode and a voltage across a diode, then you've got power dissipation within the diode. That generates heat. That then causes a temperature rise, and an equilibrium is only reached when the amount of heat coming off the diode in the form of radiation, convection and conduction, in this case through the legs, but if you had a TO220 type diode like this, then most of the heat will be conducted through the tab. The forward voltage drop on a Schottky diode is considerably better than a regular silicon diode, about 0.3 volts for Schottky, 0.6 volts for silicon. There are other problems with diode. You do get a little bit of reverse current leakage back through the diode the wrong way. You've got breakdown voltage, so that if you raise the voltage on the cathode to such an extent above the anode, then you can get a breakdown, and then a large current can flow back the wrong way. They have temperature effects. They're temperature dependent, so a lot of parameters will change depending on the temperature of the diode. You also have switching times when they're switching from forward biased to reverse biased, and you've got capacitive and inductive effects as well. So let's take a look at this 1N4005. I've got half a volt on my power supply. I've current limited this to something. What have I current limited it to? 250 milliamps, so I don't blow up the diode. Okay, let's put positive on the anode, negative on the cathode, and you can see that no current is flowing, and that's because I've only got a half volt difference between anode and cathode, and at that voltage no current flows. Let's increase this to 0.6 volts. Still no current flowing. Let's carry on up to 0.7 volts, and you can now see that a very small current of just 6 milliamps is flowing. 0.75, 20 milliamps, 0.8 volts, we've got 90 milliamps, and then once I get up above about 0.85, then of course we've got a much larger current flowing. The relationship between voltage across the diode and current flowing through it is actually exponential. And if I allowed a larger current to flow through this diode, these diodes are capable of withstanding up to 1 amp, I believe it is, for the 1N series diodes, then of course it would start to get warm and dissipate heat. And of course that's not only problematic if the diode overheats and destroys itself, but it's also lossy. You're going to lose energy just generating unnecessary heat. So to help address the main problem with conventional diodes, which is this voltage drop between anode and cathode when there's a current flowing through it, we have these things. These are ideal diodes. Now, of course, these things don't solve all of the problems of conventional diodes, but they do address that voltage drop issue, which is one of the biggest problems because, of course, it generates heat and wastes power. So by using MOSFETs, you can initially pass a current through the body diode of the MOSFET, but then if you can have some sort of system which turns the MOSFET on, you can lower the resistance of the conduction channel in the MOSFET, and MOSFETs have a linear voltage and current relationship, so they talk about an on resistance, but the on resistance of these things is very, very low, in some cases less than a milliohm. So you can reduce that voltage across the diode from sort of hundreds of millivolts to tens, perhaps even less than 10 millivolts. So let's just quickly go through these. These ones at the top here and on the right, these are older items from AliExpress. This one on the left, I don't know what it is. It doesn't seem to do anything. These ones here are P-channel MOSFET ideal diodes. And I believe these two here with the single MOSFET and the dual P-channel MOSFETs are all discrete apart from the MOSFETs. Well, they're discrete, aren't they? So these don't have an IC controller. There is a SOT23 5-pin chip there, but I believe it's just a dual transistor. This one here has a 6-pin chip and just 2 capacitors. This one I do believe is an ideal diode controller with P-channel MOSFETs. But then we come down to this bunch here, which are the newer ones. There are P-channel versions. I believe these are P-channel. And in fact, you can see the little controller chip has 2 capacitors, one either side of it. I believe it's the same controller chip as that. And then you get to the N-channel types. So you've got a single N-channel MOSFET here with a controller chip. You've got, this is N-channel, this is dual N-channel. This has a very low on resistance of around 1 milliohm, and this one is the same with the same controller chip, but it just has these high current connectors. I've got a feeling these are rated for 60 amps, but I'm just going to print out my little set of notes and then I'll go through what the controller chips are, what the MOSFETs are, and what the specs are. So data relating to these modules, I've got this list. So this is the chip marking, and they go in size order. So ZDSK is the chip marking on this little chip. And in fact, you can see that on the back of the board, they call it, it's very small, XL74610. And the chip is actually a Texas Instruments LM74610. Ideal diode controller. Now it's an N-channel MOSFET controller. The MOSFET on this little board is this AGM Semi 40 volt, 120 amp, 105 watt. It's 2.3 milliohms at 10 volts. And I don't think it actually gets 10 volts using this chip, so it will be higher than that, maybe about 5 milliohms. It's an N-channel. It's a DFN MOSFET. And I believe that means 5 millimeters by 6 millimeters. Now I'm going to come back to the LM74610 a bit later because it's the device used on these larger modules down here. But let's just look at this one. Actually, I should point out that this is a 2-terminal ideal diode. So all you've got is anode and cathode. There's no ground reference point. So you can put this in systems that have a high voltage because you don't need this to reference to ground. Now that's different to this module and this module here, which use a chip which does require a ground reference. So you can see you've got anode, cathode, whichever way around it is, and 2 ground connections here. And the chip is actually powered by the voltage between probably anode and ground. Okay, so the second one is using this DZDH0401DW. It's a SOT363. It's very tiny. It's this little chip here, and you can see that it's got these capacitors either side of it, the controller chip and a MOSFET. And this older board here appears to use the same chip. It's got those two capacitors. It's a larger format chip. I think it's a SOT. Yes, I think it's a SOT 23. But a lot of these have got their top surfaces scraped off because they don't want you to see what chip they're using. So this second one down is this module here. On AliExpress they call it an XL0401 after the 0401 ideal diode controller chip. It's 4 terminal or 3 terminal because these two are ground. I believe it will say that the top two are ground, and these are V in and V out. Now the specification on the listing says 10 amps. You can see that it's a 5.5 milliohm MOSFET, but they may not be driving it at the full 10 volts, so they may have derated it to 10 amps. They do say 15 if you've got good cooling, so I'll put 15 amps in brackets there. So this is the datasheet for the DZDH0401, and you can see that it has a max input voltage of 40 volts. So that's between the input and ground. Now I've just noticed that these two components here are resistors, and I thought, and they're very tiny, you can barely see them, I thought these two little components either side of the chip were capacitors. That's made me rethink what this controller is, so I'll have another look at that another time. But you can see that the MOSFET that this drives is a PMOS, and one of the advantages of P-channel MOSFETs is that you've got a high voltage on the input and a high voltage on the output, or a positive voltage, and you need to switch this MOSFET on, you need to take the gate to a low voltage. So this chip can pull the gate down to ground, or it's pulled down by this resistor, but it's much easier to implement a MOSFET diode up here because the gate requires a negative voltage. If this is N channel, then the gate requires a voltage actually higher than the input and output, and there are techniques for that, but I'll come back to that on the other controllers. And this XL0401 controller, they're also saying maximum 26 volts, which is not a particularly high voltage. Okay, returning to this one, the XL74610. This is saying up to 36 volts and 15 amps brackets 30 amps if you give it additional cooling. So that's the XL74610. Okay, coming down to the third module on my list. That's this one where the chip is marked 74610. Now these two that I've received subsequently are both scraped, but the one that I fitted to that little voltage controlled relay, which is now in the shed, actually has 74610 written on it, so I know that that's the controller chip for this module. All it is a controller chip and a capacitor and a couple of N channel, or on some of these modules actually you just get one N channel MOSFET. So the details are here. It's the LM74610 Texas Instruments chip. On this particular module you've got an on semi 40 volt 240 amp with a very low on resistance at 10 volts, but this MOSFET doesn't get 10 volts. It gets 6.3 down to about 5 point something, I think, because of this controller chip, and it's got N channel MOSFETs on here. Let me go to the AliExpress listing for this. So on the AliExpress listing, this module is saying 60 amps. The MOSFET itself is probably higher than that, yes, 240, but of course you can't do that because it's not heat sinked, and it's saying 40 volts is the maximum between anode and cathode. Now of course that means you've got a 40 volt maximum between drain and source, and yes, that indeed is the maximum voltage for this particular on semi FDBL 9401 MOSFET, which they're using 2 of. Now you don't have a ground reference on this. This is a 2-terminal device, so you can just use it as a diode. The diode indication is on there. Now initially what happens with this, it's very clever. I'll print the data sheet out actually. So this is the LM74610 datasheet. Now it says it has a charge pump gate driver for external N-channel MOSFET, and here's the N-channel MOSFET. Source and drain become anode and cathode on the chip. Now you can't have more than 45 volts maximum reverse voltage between cathode and anode. So you can put this in the high side of a high voltage circuit, let's say 100 volts. Ground is down here, it's not connected to the chip at all. But you do need to be careful that V out never goes more than 45 volts above V in, and that would only happen if you had, I don't know, capacitive elements on the output which held their voltage, and perhaps a smaller capacitor on the input which the voltage sank down more quickly. Then you could have V out go to a higher voltage than V in. Make sure it's not more than 45 volts. So the way this works is that current initially passes through the body diode of this N-channel MOSFET. That generates a 0.6 volt difference between source and drain, and this chip uses that 0.6 volts to power up, run a charge pump and charge this capacitor up to, I think, 6.3 volts. It then uses that supply to drive the gate to a voltage higher than source, because this is N channel, so gate is a higher voltage than V in, or the source of the MOSFET. And then if this thing goes into reverse bias, so V out goes above V in, the chip detects that and pulls the gate voltage down to turn the MOSFET off. But the issue with this system is that the energy in V cap only lasts for a certain amount of time, then it runs out and the chip shuts down. And then the current, the full current of your system is passed again through just the body diode. That then enables the chip to charge this capacitor back up. And so that's why in the beginning of this video you saw this LED pulsing. Now the pulsing was exaggerated, but I'll put that system back on after I finish this video, and we'll see that actually the off or the body diode conduction time is very short, and the MOSFET conduction channel on time is much longer. In fact, it's 98% of the duty cycle. So it only is passing current through the body diode for a very short period of time. It's not long enough for it to warm up significantly. So yes, this middle one using the 74610 is this module. Now I'm just going to jump to this module because it's using the same controller chip, and it's identical in every respect other than the fact that it's got these high current connectors here. That's the bottom module here. It says, well, I think it says ZDSK, but I don't know because it's scraped off, but it looks like it's the same chip as that. It's got a similar MOSFET. It's 40 volts, 320 amps here, 240 amps here, but similar on resistance. I'll just take a look at the AliExpress details for this and write them on here. Yeah, okay, this one is 40 amp, but that's if you've got just a single MOSFET. You can get this board with both MOSFETs populated or just one on there. And of course it's 40 volt, which is the maximum voltage between drain and source. And of course the chip itself can't take more than 45 between its anode and cathode connections. So yeah, that one is near identical to this one. And then finally, we've got the fourth one on this list, which the chip is marked either LTFKD, but all of the ones I've got are scraped, apart from this one actually, which is an older one where you can see the markings. I'll show that in a minute. That's the Analog Devices LTC4359, or if it's marked LTCXD, then it's Linear Technology LTC4357, but these are almost identical. I think 435 is just a newer variant of the chip. Of course, Analog Devices bought Linear Technology, or the other way around, I can't quite remember which. The MOSFET on there is actually a 100 volt type, 300 amps, 1.7 milliohms at 10 volts. It may not be driving it at 10 volts. I'll take a look at what AliExpress says for this module, and then we'll have a look at the datasheet for this chip. Right, yes, the AliExpress listings say that this one can take a V in of 9 to 80 volts. Can't see that very well because the lights on it, but 9 to 80 volts. Now this one does have a couple of ground connections, and the chip requires a voltage between V in and ground, so you do need to connect these to your system ground up to 80 volts, which is obviously why they've put a 100 volt MOSFET on there. This one uses this LTC 4359, and those are the details of the MOSFET that is on the board. Now they call this package a TOL 8L. I've seen on all these package data sheets this name TOL, T-O-L-L, or T0LL. 8L I presume means 8 legs. I think 7 of them along here are source and 1 is the gate, and then there's a tab on the other end for the drain. This is N channel, of course. Okay, so the controller chip here is the LTC 4359 ideal diode controller. It's got reverse input voltage protection. I don't know why you do that, but to minus 40 volts, wide operating range 4 volts to 80 volts, although the module says on it 9 volts to 80 volts. I'm not entirely sure why. So here's the application, which shows the N channel MOSFET here. You can put a transient suppression diode on the input. This generates a gate voltage, which of course for an N channel MOSFET is higher than the source voltage, which is V in. So this must have internal charge pump, but this chip does require a ground reference down here in order to operate. Now notice it has a shutdown pin, and it also says here controls single or back-to-back N-channel MOSFETs. And you'll notice here that there are 2 MOSFETs, or 2 pairs of parallel MOSFETs, with all the sources in the middle, drains are on the outside. This uses the same chip, and I can actually show you that chip. So there it is. The marking is LTFKD. And on this module, the shutdown pin has been brought out to this little pad here, and it says on and off. So this can be an ideal diode with the ability to switch it off. So it's then nothing, it's not connected at all. And that's why this particular module, which I bought some time ago, has the ideal diode MOSFETs pointing in that direction, and then these other MOSFETs which can be used to, as I say, disconnect this high side completely. So that's just one of the applications in the datasheet of this chip. It's the same chip on here, even though they've scraped it there, but it is the same chip. But on this one they've only implemented the ideal diode, in being on this side, anode, and cathode being out on that side. So if you get this model on AliExpress, they're calling it 50 amp 80 volts, and I assume it'll hold off 80 volts of reverse voltage between anode and cathode, or drain and source, on the MOSFET on that one. I'll just have a quick look at the datasheet to confirm that. Yes, on the datasheet it actually says the absolute maximum rating for in to out is minus 100 volts to 100 volts. So yes, it's based on, yes, that's what the chip will handle. And then this particular MOSFET they've chosen is this NCE power 100 volt VDS. So that can also handle 100 volts of effectively reverse bias or drain source voltage. So just going back to the 74610 ideal diode controller. At the beginning of the video I showed these LEDs going dim for quite a substantial amount of time, and this is a bit of trickery really, because I've just picked a voltage where the ideal diode is barely struggling to work because there's just no current running through it. If I turn this voltage up, it's at 8 volts only because of these 3 diodes in series. So let's go V set, take that up to, I don't know, 12 volts or something like that. And what you can see here, you may not be able to see it at all actually. No, that's too high. So let's go back down to 9 volts. You can see that they very briefly pulse off like that. Now the parameters for this chip If a significant amount of current is running through the body diode, then you will get this 0.6 volts of difference. That enables the chip to operate and charge up this capacitor. The on time is something like 2.5 seconds, and the off time is something like 50 milliseconds. If I this is only 20 milliamps. If I put more current through this controller chip, then you probably won't see this pulsing at all. In fact, you didn't see this pulsing. But this just shows that the only way that this chip can operate with no ground reference is that it has to take its power from the fact that during this very brief off time, there is a 0.6 volt, well, it's this way around, isn't it? 0.6 volt higher on the input than on the output, and that 0.6 is lost across these body diodes. The chip uses that voltage to pump up this capacitor. I think it goes between 6.3 volts at the top and 5 point something at the bottom. I'll just check that on the datasheet. Yeah, so this pulsing here, where these briefly go dim, is this. The FET's conduction channel is on for 98% of the time, assuming a reasonable current. The FETs are briefly off, which is where the current is passing through the body diode. That allows the controller chip to charge the capacitor back up to 6.3 volts. Apparently it discharges to 5.15 volts. It does say that in here somewhere. Yeah, 5.15 volts, typical. There's some stuff here on the capacitor selection. If you use a 2.2 microfarad capacitor, the MOSFET on time is 2.66 milliseconds. And the body diode on time, where the MOSFET's conduction channel is actually off, is 55 milliseconds. And you can see that 55 milliseconds there. It might be slightly elongated because I've got a slightly smaller current. So it may take a little bit longer for this chip to charge the capacitor up to 6.3 volts. But yes, it says that the duty cycle is 98%. Conduction channel on, where the gate is being driven high, and 2% where the current is going through the body diodes. So if you're looking for ideal diodes on AliExpress, then this data might be useful. These are the modules you're likely to find. I'm going to have another look at this one. These are definitely P-channel MOSFETs because I've checked them, but the chip is scraped, so I can't see what it is. But yeah, these are capacitors, which is different to the two resistors on the 0401 P-channel ideal diode controller. So not entirely sure what that is, but that's ideal diodes from AliExpress. Cheerio.